I'm Sanjay Kale. I'm a professor in computer science and I work on various aspects of parallel programming. In particular, our group's work is on adaptive runtime systems and embodied in CHAM++ parallel programming system. If you look at supercomputers and the data centers in which they operate, as well as other data centers, you find that a lot of energy is spent on cooling the computers. And we know that energy is an important cost of supercomputers, and that's becoming bigger over time. So if you're spending maybe 50%, some reports say that 40 or 50% of the energy spent on running a supercomputer is spent on cooling it. So air conditioning and so on. So if that's the case, can we somehow save it? So if you look at why we need to cool such a high degree of cooling energy, it's because we want to not make sure that our processors don't burn out. And as you run computations, they start getting hot. And so if that's the case, is there some other way of controlling their temperature? And we really, the reason the AC needs to be as high as it does is because is really to cater to the worst case. So there are hot spots in computer rooms. Some places, some chips get hotter. Some chips are slightly different than the others and they get hotter quicker. And so it is to cater to this worst case that we have to cool everything to a large degree. There are a couple of alternatives now, a couple of technologies now available that can be used to control it. One technology is something called DVFS. Using this, you can actually change the frequency at which the processor is running. If the frequency is lower, the computer will run slower, but it will get less hot. And so that's good, but how do you trigger that? Well, it turns out now chips have temperature sensors on them. So you can actually figure out while the program is running from the program itself what temperature the chip is. And if it is getting very hot, then you actually turn the frequency down and it won't get as hot anymore. Now this sounds simple, but the problem with that is that in a parallel application, you have many processors, tens of thousands of them running together, running a single application. So if you slow down one of them, they're all going to slow down because they wait for data from each other. Now this is a problem where our group has the right key. We have the technology for balancing the load dynamically. So what we do is we just change the temperature, we watch this temperature, we change the frequency as needed to cool it down, or if it is now cool enough that we increase it, and then the resultant load imbalance problem, we solve it by moving work around at runtime. For this experiment, we used a dedicated cluster set up by Tariq Abdelzar's lab at Illinois. And in particular, this cluster was attractive because it had a dedicated air conditioning unit where we could measure the energy, cooling energy as well. And then we decided what temperature we'd allow each chip to get up to as a maximum limit, and then then ran our scheme with that, and we actually managed to show that we make sure that A, the temperature of the chip doesn't go beyond the set point that we set, and B, that the performance penalty that we get is significantly small because of the load balancing that we do. We were able to show something like between 40 and 57% savings in cooling energy. There was an execution penalty, but depending on the application, it ranged between 2 and 20%. And so this is a significant saving in terms of cooling because we don't have that much impact on the execution time. Hotspots are here to stay, and in fact, we know that process variation is going to only increase as we go to from 32 nanometers to 22 nanometers and so on. As the feature sizes go smaller, we know that chips will be more and more different from each other. So some chips will get hot quicker than others. In that environment, some kind of a control like we are suggesting in this paper is pretty much essential. So I think the importance of this topic is going to only grow over time, not to mention the fact that as we get to build larger and larger machines, the amount of power that we are supposed to require and fit within the power budget will also require us to pay more attention to issues such as controlling power explicitly through software while the application is running. What I would like to have happen with this paper is that there are many people who are looking at DVFS. I think we bring a new aspect to the table, which is basically the adaptive runtime system. That controlling frequency just by itself is not enough. You have to actually do this, couple it with this dynamic load balancing, and we have that piece of the technology. And so we would like to join the set of people who are working on the energy issues and try to get them interested in the adaptive runtime system aspects from that point of view.